Hello, my name is Anton and today I'm going to be presenting you our new algorithm for the human force capacity evaluation based on the musculoskeletal models. With the increasing number of collaborative and assistive robots, many of their control strategies are becoming human-centered, requiring the robots to continuously adapt to the needs of the humans involved. The fundamental challenge for any of them is to be able to measure or estimate in real time some performance or capacity metrics for humans. One of the very well-known capacity metrics, both in terms of safety and performance, is a wrench or a force capacity, the ability to apply and resist forces in different directions of space. This metric is very important because human force capacity is not constant, which we all know intuitively. If we are carrying an object, even though its mass is constant and the force of gravity doesn't change, we all know that in some poses of our arm it's much easier to carry the object than in the others. Now, instead of a baguette in our hand, if we consider a generic force applied to a certain part of our body, this force will generate certain torques in our joints. Using our muscles, we can resist this force by producing exactly opposite joint torques. However, due to different biomechanical or biological factors, our muscle forces are limited, which means that the set of all the forces that the human can resist is limited too. And this set of all the possible forces that the human can generate given the limitation of the muscular forces is called its force polytope. And the shape and the size of this polytope will change based on the pose of his arm. The mathematical structure of this problem is challenging though. The problem first needs to be transformed to a different form, suitable for example for control or visualization use cases. Because of the usually large number of muscles considered in the musculoskeletal models, often more than 50, these polytopes have very complex geometries, making the standard exact methods very impractical, having execution times of several hours. To overcome this, we have developed a new iterative algorithm able to approximate the polytope while guaranteeing user-defined accuracy. This algorithm uses the linear programming to find new vertices of the polytope, followed by the convex-hull algorithm to group them to faces. By repeating this sequence, we successively improve our approximation accuracy. The algorithm will continue iterating until the maximal distance between the approximated and the target polytope is within user-defined value. This way, the user can intuitively trade off the accuracy for the execution time and bring this metric to the real time. In this video, we can see real-time force polytopes of the human operator's arm on the right. Human arm is modeled as 50 muscle 7 degrees of freedom musculoskeletal model, and the algorithm execution time is 200 milliseconds. In the experiment from the video, human operator and the robot jointly carry 7 kg object. And the robot uses the human force capacity polytope to determine his carrying capacity in real time. Using this metric, the robot is able to ensure that the operator's carrying capacity is not exceeded, even though the operator freely navigates the objects through the common workspace. More details about this experiment and the algorithm itself can be found in the paper. Finally, an efficient Python implementation of this algorithm can be obtained using only one line of code, pip install PyCapacity. Thank you.